All right, we made it to our last page of this review. We're going to get into some equation solving and just a couple things unique to each of these problems that we want to look out for. So number 23, we're going to solve for x. So x is an exponent, x up here is in the exponent, but what we want to notice is that we have this equation where 5 to this power is equal to 5 to this power. So if you're solving an equation and these two are equal to each other, if they already have the same base, that means that they will also have the same exponent. And that's what we can work with. We can set the exponent of x plus 3 equal to the exponent of 2x minus 1. We're allowed to do this only if the bases are the same and if that's all that you have on each side. 5 to a power is equal to 5 to a power. Well, when those bases are the same, we get to work with the exponents. So now we have a new equation, x plus 3 equals 2x minus 1. Pretty straightforward. We'll just get the x's to the same side. So subtract x, we've got 3 equals x minus 1. And then just adding 1 to both sides, we're getting x equal to 4. And we're done. We have solved for x. Now, 24 is kind of similar, but not exactly. We don't have the same base, right? The base is 1/3 raised to the x minus 6 power, and this base is 9 raised to the x power. So can we manipulate this equation in any way so that they are the same base? Because if they're the same base, we do what we did on the last problem, and then that's pretty straightforward. So one thing that we can do with this left side of our equation, this 1/3, I would like this 3 to be in the numerator and not the denominator. We're allowed to do that. I can take something in the numerator, move it to the denominator, and vice versa. What it will do though is it will change the sign of your exponent. So in the denominator, that 1/3, the 3 in the denominator has an exponent of 1. When that moves to the numerator, it becomes 3 to the negative 1 power. So that 3 to the first, with that movement, just changed the sign of the exponent. And then raised to the x minus 6 power. So what we have here is a base of 3 raised to a power raised to a power. So when we have a power to a power, we can multiply these exponents. So we have 3, it's going to feel like distributing -1 times x, -1 times -6. All right, so there's the left side of the equation. Now the right side is 9 to the power of x. It'd be really tempting to divide by 3. Like, let's just take the 9 and divide it by 3 so we get the same base that we have over here. Well, we can't do any operations to the equation because if I divide by 3 on one side of the equation, then I have to divide by 3 on the other side. But we're allowed to manipulate. We're allowed to replace and substitute things of the same value. What we did here, when we moved this 3 to the numerator, we didn't change the value of anything. 3 to the -1 power is the same thing as 1/3. Those are the exact same thing, just written two different ways. So this 9, what we are allowed to do is, can we replace it with anything? And on the left side of our equation, we're working with a base of 3. So that 9, we can replace with a 3 squared, because 3 squared has the same value as a 9. I didn't change the value of anything with an operation. We're just swapping out the same thing. We're just writing it a different way. So instead of 9, we're going to write it as a 3 squared, and that's being raised to the power of x. And now we have 3 raised to a power to another power. So our exponent property tells us we can keep our same base, but then we will multiply the exponents. 2 times x is 2x. Now we've got an equation like the last one, where we have the same base. 3 to a power is equal to 3 to a power. Because the bases are the same, that means that our exponents will also be the same. So we get to work with the exponents. Negative x plus 6 is equal to 2x. When you have x's on both sides of your equal sign, let's get those together first. So we have 6 is equal to 3x, and then divide both sides by 3, and we're getting x equal to 2. All right, so 23 and 24, that's working with exponent form. When you're in exponent form, if you have the same base equal to each other, the exponents are equal to each other. Well, 25 and 26, these are not exponent form, this is log form. So if you have the same logs, when I say the same logs, I mean log with the same base. So here's a log base 2 of 2x is equal to a log base 2 of x plus 3. So this log base 2 is equal to this log base 2. Well, if the logs are equal to each other, then that means that what we're taking the logarithm of must also be equal to each other. That 2x has to equal the x plus 3 if those logs are equal because of that equal sign. So that's the equation we can work with to solve for x. So to get x alone, or I'm sorry, like x is to the same side, we're going to subtract x. So we have x equals 3. Done. All right, number 26, again, we're in log form. So let's check our logs. There's a log base 5 of something is equal to a log base 5 of something. So we know that, log base 5 is equal to this log base 5. So that means that what we're taking the logarithms of must also be equal. So we're going to write our equation, x squared minus x equals 2x minus 2. All right, so when we see this equation, what we want to notice is we have x squared and we have x. When we have x squared equations, we're going to try to solve this by factoring. We know we can default to the quadratic formula. Either way, we want to get everything on one side of the equal sign, so we have 0 on the other side. So I'm going to subtract a 2x from both sides. I'm also going to add 2 while I'm at it. 2x minus 2x, negative 2 plus 2. So we have x squared. Combine those x's, we get minus 3x. And then that plus 2 is not a like term with anything, and that equals 0. All right, well, let's try to factor first. Do we have factors of 2 that add up to negative 3? And we do. X minus 2 times x minus 1 equals 0. So now that it's factored, we use our zero product property to set each factor equal to 0. X minus 2 equals 0, x minus 1 equals 0, and then solve for x, and we get a positive 2 and a positive 1. All right, last two problems. Okay, so it just says write the first 4 terms of each sequence. So this is an explicit formula. The way that the explicit formulas are set up is this is going to be our first term, that's our A1. This is our common ratio. This is a geometric sequence. That means that we are multiplying by 7 to get from term to term to term. We always multiply the last term by 7. So when they tell us to write the first 4 terms, we want to recognize that our first term is 2/3, and then we're just going to multiply that by 7. 2/3 times 7 is 14/3. 14/3 times 7 is 98/3. And then the last one, 98/3 times 7 is 686/3. Those are the first 4 terms of the sequence. I'll just make a note, that is an explicit rule right there. All right, last problem, number 28. This is a recursive rule. Well, I guess I'll write that down since I just wrote down explicit. Now, in a recursive rule, this first line right here, it says an equals 5 if n equals 1. When they say n equals 1, that's your first term. That means our first term is a 5. So we're going to start out with a 5. Then they're telling us right here, take a n minus 1, that's the previous term, and multiply it by 4. When it says if n is greater than 1, that means for all the terms after 1. So we're just going to take the previous term and multiply it by 4 to get the next term in the sequence. So 5 times 4 is 20. Now we take the 20 times 4 is 80. And then we take the 80 times 4 is 320. And there we have the first 4 terms of that sequence. And that's it. That was the fastest page. All right. Hope that helped.